Welcome to today's webinar. The topic today is Advanced Structural Analysis with RFEM 6 Python API. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the content of the website, the German and English webinars, newsletters, customer projects, and so on. I will be the moderator today, and I will be supported by my 3 colleagues. Dogu-Khan will do the presentation, and my 2 other colleagues will support us with answering your questions, but my 3 colleagues can introduce themselves.
Yeah, hi everyone. My name is Dogu-Khan Karataş, and I'm the technical product manager at Dlubal Software. I'm leading the team who's responsible for API and AI development, and I will be the representative of today's webinar.
Hello everybody, I'm Miroslav Broz, and I'm the tech lead of the teams which are responsible for the development of APIs, web applications, and the interfaces. And today I'll be replying your questions which you could have during our webinar.
Hello, my name is Rebecca Goebel, and I work at Dlubal in the development for web service and API. And I also work in customer support, where I mostly answer customer questions regarding web service and API. And today I will also answer your questions.
Okay, thank you for your introduction. Then we can switch off our webcams that the attendees can see the full screen. I say some words how you can ask questions, at least for the attendees who participate the first time. On the right side of your screen, you see the control panel. You can show that with that arrow here, and then you can enter the question here. Yeah, and we will answer you. You can also watch the entire webinar and then email your questions afterwards to info@dlubal.com. Yeah, and then you will get also an answer via email. Okay, then I hand over the screen to Dogu-Khan. Just a moment. Dogu-Khan, it's your turn.
So yeah, I hope everyone can see my screen now, and
Yes.
I'll start with my presentation. Okay, so today, first I'm going to start with a small presentation about web services and API. Then I'm going to go create some live coding examples for you. So let's start. First, what I would like to do is to start with a small overview of web services and API technology. I already explained the logic of this technology on our previous webinars, but I want to go through it again in case there were some new users among the attendees. For those who may not be familiar with programming, don't worry, I will guide you through every detail step by step, making it easy for you to understand and operate. As a team, we at Dlubal Software are continuously developing frameworks to simplify your programming experience in RFEM or RStab or our other products. As you know, the goal of this technology is to provide you an easy-to-use programmable interface for structural analysis. So today's topics include, as I said, an overview of web services and API, and the main logic behind the technology, as well as how they work in practice. And then I would like to mention our recent developments in our API library, what is new, what to expect in the future. And also a comprehensive overview about our library and development community. As you know, we are committed to keep our ongoing development open source, and we know the value of our community. Therefore, I'll talk about how you can be a part of our community-driven development. And lastly, 2 live coding advanced examples to help you understand better how to use our technology in practice in real-life projects. In the first example, I will create a 2-story building and perform a model analysis to get the natural frequencies. And in the second example, I will analyze a steel beam constructed by surfaces, and then we will analyze the meshing and stresses, and then visualize our project in a web application. Yep. So let's get started. I also want to talk 3-4 minutes about API and web services technology. So API stands for Application Programming Interface, which is a set of rules and some protocols that software programs can follow to communicate with each other. It acts as a messenger and facilitating the exchange of information between different programs or services by receiving requests, translating them, and returning responses. It enables the smooth transfer of data functionality between different systems. So to illustrate this concept, I always give this example as you are the RFEM users, right? You open your RFEM 6, you give some commands with the graphical user interface. You use your mouse, you use your keyboard, and you click somewhere, give some values. So this is the communication between RFEM and humans, right? So the interface is our graphics. And in API is in the same way, an API allows software programs to interact with each other by providing a standard set of rules. So as you create a Python program, you also communicate with RFEM, but you don't have to touch your mouse and do anything. Just click on Run Python. Yep. So if API is this, so what is a web service? Yeah? Web services are a type of APIs, but the difference is that the style and the way of communication. Web services facilitate XML-based information exchange between the systems. In our case, we use a HTTP technology called SOAP. So it stands for Simple Object Access Protocol, and which provides a standard method for accessing web services. But this HTTP protocols gives us some XML, but it's not usable by the end user really. So our team has developed frameworks that enable the use of this connection in structural analysis and design. These frameworks provide basic functions that allow users to send commands to RFEM and receive some responses. They are designed to be user-friendly, so even users with minimal experience can use them effectively. So this was the overview about web services and API. If there are some newcomers, so what I want to show is now, in this section, I would like to highlight the new features we have implemented and emphasize the important points mostly requested by our users. The first development I want to share with you is the calculation in cloud is available via our API now. As you can see, now you can select one of the servers available inside your script and send your calculation to the application server, even without opening RFEM at all. Now you can choose to get an email notification and track your calculation through our extranet. This is a great feature, in my opinion, to integrate RFEM solver to your existing workflow. With this, you can run calculations in the background. And the second point I want to emphasize is now it's possible to access mesh points data via our API. You are already able to see the mesh table inside RFEM 6. But the big advantage of API is now you can access the deformed mesh points coordinates also, which is not possible through our graphical user interface. I'm going to use this function in one of my examples today to play with mesh data a little bit. And lastly, most exciting one in my eyes, we have developed our chatbot assistant using large language models. We trained a large language model in our data that we are building for years. Now we can ask anything related to the Dlubal software, finite element analysis, or any question you can imagine about structural analysis, and Mia is going to help you with that. Mia is directly integrated to our website. You can access Mia through our website, or it's directly integrated in RFEM itself too. So there are 2 points that you can access Mia. Okay, after the latest developments, now I'll show you our library and community-driven developments. As Dlubal Software, as I said, we're committed to keep our ongoing development open source and collaborate with our users. Our whole API development is public in GitHub, and is accessible to everyone. In our GitHub page, we are getting in touch with our users, we are supporting them with their questions, and also they're supporting us with their contribution. I would like to invite everyone in this webinar to our repository in GitHub and be a part of our community. Also, we have a documentation website for our external developers. How to get in this website, we have articles about how to get started, how to install the library, and all the necessary insights. Also, we have explanations for every class and method. I kindly ask you to visit and take a look. You can find the link in our GitHub repo. Yeah. So that's it with the presentation. Let's quickly jump into the real-world applications I wanted to show you. So in this webinar, I'm going to use a Visual Studio Code. I'm going to open my webinar examples. Yes. So as you can see, I downloaded my model here. So library here. Here's the RFEM library I would like to access, and also you can access it via pip install. But I wanted to use it from a local directory for this webinar. But as I said, if you want, you can use it via pip too. So it's accessible from everywhere. So first example, I'm going to show you a dynamic analysis of a 2-story concrete building. So I'm going to create a Python file here. Yes. So I opened my RFEM already here. And in the options, program options, use web service in application is enabled and server port range is true. Okay. So first thing I need to do is to import my necessary libraries. I'm not going to write them from the scratch, so I'm just going to copy and paste them. I prepared it beforehand. So as you can see, first I'm importing the enumeration items, all of them. Then I'm importing the model class, calculate all, set add-on statuses, and so on. And all the basic objects I need, material, section, thickness, node line, etc. And also some static analysis settings. I think I wrote it twice, so I don't need that. Load case and model analysis settings. Also, I have some loads, surface load. And then to access the result, I'm using our result tables class. Okay, so first thing I would like to do is to call my model class, and I'm going to give an argument true, which means create a new model. If you want to access an existing model, you should call it false. And then I'm going to give the name of the model I'd like, so dynamic analysis. And then I'm going to put just a classical Python checker if I'm running directly inside the script or I'm importing something. So it should be main. Okay. So now I can start to write my code. The first thing I would like to do is to activate my add-on for model analysis, because in default they're not activated. So I'm calling my set add-on status function from init model, and I'm calling my client model here, and add-on equals to add-on enumeration.model. So model active stands for the model analysis. And then lastly, I'm telling status, so turn it on true. So this should be activating my model analysis settings. Then I'm going to create my material. Oops. Yeah, it's the material, and the name of the material is C3545 concrete. And then I'm going to create the section, which is the first section, and the name is SQM1 0.25, which means 25 centimeters by 25 centimeters, a concrete section. And then I'm going to create 2 thicknesses. The first one is for ceilings, and I'm going to use the material. As you can see, when I create something, when I call a class, so I'll do it from the scratch. When I call a class thickness, when I open up my parentheses, you can see which arguments you need to give, namely, yeah, the first thing is the number of the thickness, so it's 1, and the second is the name, so I'm calling it ceiling, and the third one is the material, so you need to pass the material number. So I have this concrete material number 1, so I am giving 1, and the uniform thickness, D is a float, so let's select 0.4 for ceilings and another thickness for walls, yeah. And the uniform thickness, first I need to give the material also. This is the material number 1 and the uniform thickness of 0.25. Let's select. Yeah. So I created my materials section, thickness, blah, blah, blah. Then I need to write some basic geometrical functions to create my geometry for lines. But it's somehow lots of for loops. So I don't want to write it down from the scratch because it's maybe so boring for you. So I'm just going to copy and paste it. Also, yeah, here. So let me explain to you. I set some length, width, and height, and then I'm running some for loops for nodes. This for loop is creating the necessary nodes. This for loop is creating the necessary lines. So these are basic geometrical applications. This is for vertical lines. This is for horizontal lines. Then finally, I create my surfaces and also the members. So if you want, let's check in RFEM if my structure is truly assigned or what. I'm going to split my monitor. So let me run this. So I used Shift and Enter to run this program. So every time you run this program, you will see the connecting to server. The other thing you need to see is that there should be a connection in RFEM. As you can see, now my dynamic analysis model has been created. New model is open. And then, yes, application is logged by connection of an external application. This external application is my Python program, apparently. So as you can see, now the lines has been created, materials, and then surfaces and members. Done. So my geometry is right here. Nice. Yeah, after the geometry, now I think I can jump into what I need. So first I need the boundary conditions. So I would like to assign some line supports and node supports. So I'm going to call my line support class, and it says to me number of the line support. So it's the first one, and then I can assign the lines. So let me check which lines I need. So 37, 34, 33, yeah, 36. So it's from 33 until the 38, sorry. 35, 36. Yes, and then I can select my support type. So I'm going to use hinged. As you can see, I already defined, when we are creating this library, we defined some default values. As you can see here, the default value is hinged. So if I just leave it empty, it will know I want to use hinged. So I don't need to create something else from it. Now I go to nodal support. It's nodal support 1, and which nodes I would like to assign here, 8. What's the member now? 4 and 12 here. So 4, 8, 12. And then it's same, but just for showing, you can just call nodal support type, and that, as you can see, there's fixed, free, hinged, roller, and so on. So I'm going to select hinged here. I'll run it again to check if everything is correct. So application is logged, and I assigned my nodal support. Maybe you, there could be a question from this part, because in the model, where is it? Yes, in the model class. So I told the program through dynamic analysis, so create me a new program. But we added a new feature that if if you're calling an existing application, no matter what, if you write here true or false, it will automatically know which model to connect. So it's not going to be closed and write it again, so you don't have to wait again and again every time you run your program. Okay, after the nodal supports, I would like to create some analysis settings for static analysis settings. So as you can see, there are lots of attributes for static analysis settings, but I'm just going to use the default ones. Also for model analysis settings, I'm going to use a default model analysis settings. After that, I would like to create 2 load cases. The first one is that, so I'm going to assign some dead loads. Also, I'm going to think about the self-weight too. So for this, as you can see, there is an attribute of self-weight. So there's a list. I'm going to open my list. So I'm going to tell true, yes. Consider the self-weight 2. Not on X direction, 0, not on Y direction, 0, but in Z. So 1, yes. So that means take into consideration the self-weight in the Z direction. So lastly, I need to assign an action category type, which is a permanent G for this case, yes. As you can see, for all the enumeration items, we already assigned all the enumeration items to a class, so you don't need to write it from scratch. When you use dot notation, you can see all types of action categories inside the library, and you don't need to write it from scratch. I know it names something like permanent and G, and I can just write some letters and it's here. And then, yes, and then I'm going to create my load case for the model analysis. So this is the load case 2, name is model, and then the action category is equals to, yeah, I can use it, action category type, and I'll select seismic action. And then lastly, you can give a parameter to check the analysis type. So I'm going to use the params dictionary. So params dictionary is the magic for our development, because that means in this dictionary you can give every available web services comment to a class, even we didn't create something inside the high-level functions. Now, for example, I'll change the analysis type as analysis type model. Yes, it should work, I hope. And then after that, since I have load cases, I can create a surface load, I believe. So surface load 1, I'm going to inherit it from load case 1, and I'm going to assign it to the surfaces for ceilings. So this is surface number 1, this is surface number 8, yes, so 1 and 8. And then let's select 5 kilonewton per meter. Per square meter, yes. And then I'm going to calculate all, but before, let me check if the loads and analysis settings assigned correctly to our model. So I run the script again. No, so there is no analysis type. Maybe I made a typo here. Let me check here. So yeah, there's a typo. Let's try it again. Yes, so everything is here. I will turn on my loads, yes. So 5 kilonewton per square meters. Yes, so everything looks cool. I can start my calculation. Then I can read my results also. So I'm going to call my calculate all function. It will calculate everything. Then that means I can access the natural frequencies. So let's create a variable called natural freq and call our result tables. dot notation. So I would like to reach model analysis, natural frequencies. Yes. And then the object type is a load case. So model analysis is a load case type. I don't need to change it, but I need to give the loading number because the model analysis is loading number 2, but in default it's 1. So I changed it as 2. And if you want, let's print it to the console. So printing is the best debugging in Python. So let's try it. Yeah, so yeah, connection is started, and then we're expecting the mesh. Yes, and mesh is done. Now the calculation has started also. And yes, I printed my angular frequencies, eigenvalues, natural frequencies, and also the natural period, of course. So as you can see here, now you can go to the model analysis. No, not static analysis, model analysis. Yes, here. So this table, I can access this table in my Python script. If I run this solver in the background without any GUI, I can still have the access, and I can play with this dynamic analysis data, as you can see. Yep, that was all for my first example. I will jump quickly into the second one. So what I'm going to do is first I'll close my terminal, maybe close this model 2. And then I am going to create a steel beam for you constructed by surfaces, and then we will analyze it. So yeah, let me just copy and paste the imports too. I don't want to write them all over again. I imported the model class, calculate all functions, some base settings, and basic objects are node, lines, materials, and so on, and supports. And the different thing is now I imported my mesh settings, so I can change my mesh setting in every calculation, and also from result the mesh tables to access the mesh tables. Also, I imported the external Python module pandas to handle with data, and I'm going to visualize our project using plotly library. First things first, call the model class true steel beam surfaces that are. In this string, if you want, you can give the ref6 or not, so it will automatically understand what's going on, so it doesn't really matter. And I would like to add a service call, which is delete all. That means every time I run this script, everything will be deleted and will be created again. So I don't want to have some errors because of overwriting. And since I'm going to visualize it, I'm going to change a base setting. So in RFEM, when you create a new model, so there is always a chance in the settings and options for local access. I'm using my GUI set downward, but in programming, I prefer the orientation Z up because it's always easier to use, I would say. So I'm going to change this base settings using my base settings class. So global access orientation is equal to global access orientation type Z up. Yes, so it will change the global access orientation. Yeah, so what I need to do is to create some nodes and lines. So I prefer to get them also. I don't want to write them from scratch here. So it's so boring for you. So as you can see, I have 12 nodes and 16 lines to construct a simple varying cross-section tapered beam. So I'll run and let's check the geometry first. Yeah, I'll create a new model called steel beam surfaces. Yes, as you can see now, the global axis set is upwards and my model is created. So I'll zoom in. So yes, this is my tapered beam, which I want to analyze. That's not my beam actually, it's just lines. So I'm going to assign some thicknesses to them. First, I need a material. I'll select S235 steel material. And then I'm going to create two thicknesses. One is for web. And the material number 1, I assigned a uniform thickness for web. Let's select 0.01. And the thickness 2 is for flange. 1 and then 0.016 for it. Okay. So after that, I'm going to create surfaces. So surface 1, surface 2 for upper web, surface 3 for upper flange, surface 3 for web, and 2 more for the flange here. So let's create this first surface 1, and boundary lines should be, so we can start with this or here 13 to 11. Okay, so here is 11 1 let me check 1 11 12 6. Okay, so it's 12 6. Yes, the boundary lines, and the thickness is 1. So the second surface could be something like, where is the, yeah, checking the line numbers. Yeah, 7 11. Okay, so the second one should be 3 11 8 and 14, but yeah, there is no commas. Yeah, just spaces. And I'm going to use thicknesses 2 and surface number 3. What do I have? 2 13 7 11. Thickness 2. The other surface, okay, here now up is 5. Okay, 5 16 10 12. Thickness 2, and my last surface. I know this process a little bit boring, so I just want to speed it up a bit. 9. It should be 15, yes. And thickness number 2. Okay. Oops. And let's run it. Yeah, lines has been created, and let's check the surfaces. Grid points cannot be equals to 0. So where's the problem? Yeah, let's check. Surface number 5. Yeah, it's not created, just the number 5. Let me check why. 12 4. Okay, it's 9, not 8. Okay, just run it again. I made a mistake there. Let's update it and see. Yes. So yeah, I have my surfaces. So I created this tapered beam with surfaces, and let's add a line support. So I'm just going to add the line support to the web. So it's a hinged beam. Line support class 1 and lines number. Which line is it? It's the line number 1. Yes, and line support type fixed. Okay, then I'm going to add a load case. I will just use the default one. And I can create 2 nodal loads. Yeah, my plan is to create 2 nodal nodes on this point. One is on Z direction, one is on Y direction. Yeah, the first nodal load is going to be load case number 1 and will be on node node 8. Yeah, and then the nodal load direction is going to be global Z. And then let's give minus, I don't know, I'm going to give a big number to see the meshes and the deformations good. So let's go to the other nodal load. It's nodal node 2 actually, on node case 1, on node 8, and nodal load direction is global Y. Let's give 2000. Yeah, or 20,000. I have my nodal loads. So yeah, next thing I would like to do is to play with meshes a little bit. There's a default value for the mesh settings. So target length of finite elements is 0.5 meters. I would like to play with it a little bit. So let's create a variable called mesh length, and it's 0.5 by default. And then I can call my mesh settings. Common config is the configuration dictionary for it. I'll give my general target length, length of FE is equals to mesh length. Yes. So let's give it a try and calculate all to see the meshes. So generating mesh has started. So yeah, as you can see, it's not a really fine mesh because it's 0.5 meters and it just meshed it into the 4 sections. Yeah. But if you want, let's first finish our setup, then we can play with the mesh length a little bit and see the differences. Yeah. So after that, what I wanted to do is to access all the mesh tables. First, I would like to get all the mesh surfaces. So let's create a variable called all surfaces is equals to mesh tables get all 2D elements. And then let me store this data. Let me store this data in pandas data frames. Yeah, it's the best way to store data in a pandas data frame. All surfaces, yes. And then I'm just going to change some type of my surfaces. So surfaces equals to surfaces. Open up my parentheses. And I think I need one more parenthesis here, surfaces again. And so, no, not surfaces again. So I need to give some column names, surface number, if E, node number 1 number, if E, node number 2 number. So it's a surface. So I need 4 nodes actually. So let's just copy and paste. Just change it to 3, yes. And 4, yes. And I would like to change the types to the integer, so I'm going to use this, yes. And next thing is I'm going to access all the FA nodes. Yeah. So I'm going to create a variable all FA nodes is equals to mesh tables and get all FA nodes. Yes. And then I'm going to send this to a variable called mesh nodes is equals to pandas data frame and get all FA nodes. Yeah. So I know this is not a structured data, so what I want to do is structure the columns again, but it's easier in here. Mesh nodes is equal to mesh nodes and X, Y, Z. I just need this tree. And what I want to do next is to access the deformed mesh nodes. Yeah. So this one is the here, as you can see. But when you turn on the result, also there are some deformed mesh nodes, as you can see. So it's basically, let me split it again. Yeah. Basically, what I wanted to do is to access the deformed mesh nodes too. So deformed mesh nodes is equals to sorry, let's first take the all FA nodes deformed. Yeah. So let's call it like this and access the mesh tables and get all nodes, all FA nodes deformed. This is the table I would like to access. Then I can create a deformed mesh nodes inside a pandas data frame, all FA nodes deformed. Yes. And I'm going to structure it again like this and change it with deformed mesh nodes. Cool. Yeah. Yes, now I think I have it all. And let's give it a try and print all FA nodes or mesh nodes. Yep. And then let's say print here are the mesh nodes and print here are the deformed mesh nodes. And then I'm going to print the deformed mesh nodes. Oops. Deformed mesh nodes, yes. Let's give it a try. I'm going to run my application. And I would like to access all the mesh node coordinates which is deformed under our loads that we defined, the nodal loads. So we will check if it's working or not. Let's see, meshing has been done. Yes, it worked, yes. So let's check the terminal. So yes, here are the mesh nodes. As you can see, there is 30 of them because it begins with 0. Here are the mesh nodes, and here are the deformed mesh nodes. Here are the coordinates of the deformed mesh nodes. Great. What I want to do next is to visualize this data in a web application using Plotly. I'm not going to write it from scratch again. So I just wrote a function. I'm going to copy and paste this function. I'm going to explain this to you. So yes, I make it bigger. Yes, so I created the function called plot. So it creates the vertices on X, Y, Z, and then it creates the faces inside a for loop and the triangles, because Plotly just allows us to create meshes in triangles. So we are creating 2 triangles for a surface. And then I create the mesh object with vertices and creating some edges, and finally the layout, the camera, and blah blah blah. They're not so important. You can take a look at the Plotly website and you can update them if you want to. What I want to do is now let's just show these figures. So undeformed thick is equals to plot mesh nodes. So I'm just giving the node data frame inside my plot function, and deformed thick is equals to plot deformed mesh nodes. Yep. Let's run it again and see if it works. It should create 2 web pages for us with the 3D render. Let's check the RFEM in the site. We have printed them, yes. And oh, I forgot to tell to show them actually, so I needed to add this show deformed pic.show. Yeah, we'll run it from scratch. Yeah, check the RFEM again. Model has been created. And now we will see this data frames printed in the terminal again, and then I hope 2 web renders. Yes. So as you can see, now I created this web render with Plotly, and this is for undeformed mesh, and this is for deformed mesh. As you can go through the nodes and check how much deformation for every node is. And yeah, as I said in the beginning, this mesh is not really refined, so you can go through your script and tell, okay, 0.5 is too big, so I want to do it 0.1, and let's close them. And I run my server again. Since I added this service delete all function, it's going to be created from scratch every time. This is something I'm doing in purpose to not get any overrides. Yes, now I have a little bit more refined meshes. Here is the coordinates of the undeformed shape. Yeah, and here is the coordinate of the deformed shape. So the idea is you can use the RFEM in the background, and you can create some web applications with surfaces, with deformation and all. And there are some tools in Python. You can find them open source. You can add a scale like we have in RFEM. Yeah, you can add a scale. Where is a scale? Yes, here. So the control panel, you can see the global deformations, and it's also possible to add in Python too. So it's a bit complex, so I didn't want to show it today. But the main idea is that with our Python API, so there are endless possibilities you can do. You can create your own applications however you want. Yes, that's all from my side. That was the end of the second example. I hope everything went smooth for everyone who attended. And yeah, thanks for joining. And I give the word to the Andreas.
Okay, thank you, Dorukan, for this nice presentation. Before I show you on the website where you can find the recording in the next days and then the models and PowerPoint slides, I would like to give you a hint. If you want to book your free online appointments, such as a product demonstration or something like that, yeah, just contact our sales team. You can click on that link in the PowerPoint slides or scan that QR code. Also, when you have got or want to get a non-binding offer or something like that. Okay, then I switch to our website under dlubal.com. Then under news and events, you can find the events here and the webinars. Those are the webinars of the next weeks. Next week, linear stability analysis. Then we introduce in the week after next week the RFEM 6 to T-class structures interface, our regularly webinar, most frequently asked questions, and so on. Let me search for today's webinars. It's also already a previous webinar. Just a moment. We have already planned a lot of webinars. That's today's webinar. I click on it. In the next days, you will get an email with a direct link to that page here. And then you will find the recording in the middle. Then you will find the presentation slides. They are already there. Also the Python source codes of the examples. Okay, that should be all that you need to go through the webinar later. Okay, that should be all also from my side. Thank you for your attention. Thanks to Dogukan for this nice presentation. Thanks to my two colleagues, Jaroslav and Rebecca, for answering a lot of questions that come in our webinar. Okay. Then have a nice rest of the day. Maybe we meet each other in a future webinar. Bye-bye.
Have a nice day. Bye.